The universe is not just expanding, it is accelerating. Every galaxy is racing away from every other, faster and faster, as if space itself is being stretched by an unseen hand. This discovery shattered our cosmic understanding. It revealed that the vast majority of our universe is made of something we cannot see, touch, or explain. A mysterious force we call dark energy dominates everything, and we have no idea what it is. Today, we will confront the 25 deepest, most perplexing questions about this runaway expansion. By the end, you will grasp the true scale of the mystery that defines our reality. We will ask if gravity itself is broken and if our universe has a hidden direction. What does it feel like to live in a cosmos where the fundamental rules are still being written? Our journey begins with the most fundamental question of all. What is dark energy? To understand the depth of this mystery, we must travel back to the late 1990s. Astronomers were observing distant cosmic explosions called Type 1, a supernova. These are not just any stellar blasts, they are remarkably consistent. A Type 1, a supernova, always explodes with the same intrinsic brightness. Think of them as cosmic lighthouses. If you see a lighthouse in the distance and it appears dim, you know it must be very far away. By measuring how dim these supernovae appeared, scientists could calculate their distance with incredible precision. And by studying the color of their light, they could determine how fast the universe was stretching when that light began its journey billions of years ago. The expectation was simple. The gravitational pull of all the matter in the universe should have been slowing the expansion down, like a ball tossed upward, gradually losing speed. But the data told a shocking opposite story. The most distant supernovae were fainter than they should have been. This meant they were farther away than anyone predicted. The expansion of the universe was not slowing down, it was speeding up. Something was pushing galaxies apart, fighting against the relentless pull of gravity. This discovery in 1998 was so profound it won the Nobel Prize, but it left physics with a colossal problem. To explain this accelerating expansion, cosmologists had to invent a name for the culprit. They called it dark energy. It is crucial to understand what this name represents. Dark energy is not a substance we discovered. It is a label for our ignorance. It is a placeholder in our equations, a blank space where an answer should be. We can describe what it does. It exerts a negative pressure, stretching the fabric of space itself. And we know how much of it there is. Measurements from the cosmic microwave background and other probes tell us that dark energy constitutes about 68% of the total energy budget of the entire cosmos. To put that in perspective, all the stars, planets, gas, and dust you have ever seen or heard of, all the normal matter, makes up less than 5%. Even the elusive dark matter, which binds galaxies together, accounts for about 27%. Dark energy is the dominant component of reality. Yet its true nature is a complete enigma. Is it a property of empty space itself, a cosmological constant as Einstein once suggested? Is it a dynamic field that changes over time? Or is it a sign that our theory of gravity, Einstein's general relativity, breaks down on the largest scales? This is not a small puzzle. It is the greatest unsolved problem in modern physics. The force that controls the ultimate fate of everything is a question mark. The simplest explanation for dark energy is a ghost from the past. When Einstein first formulated his equations for general relativity, he faced a problem. The universe, as understood at the time, was static and eternal. But his beautiful equations predicted a cosmos that should either be collapsing under its own gravity or flying apart. To force a static solution, he introduced a fudge factor, a repulsive force woven into the fabric of space itself. He called it the cosmological constant. Years later, when Edwin Hubble discovered the universe was indeed expanding, Einstein famously called this addition his greatest blunder. he removed the constant from his equations. But the discovery of cosmic acceleration brought it roaring back. A cosmological constant, a fixed energy density inherent to empty space, perfectly explains the accelerating expansion we see. It is elegant, simple, and fits the data. There is just one catastrophic problem. It makes no sense at all. According to our best theories of the small scale, the quantum world, empty space is not empty. It is a seething, bubbling foam of virtual particles constantly popping in and out of existence. This quantum frenzy should endow every cubic centimeter of the vacuum with a colossal amount of energy, a vacuum energy. And this vacuum energy would act exactly like a cosmological constant, pushing the universe apart. So we have a prediction from quantum physics and a measurement from cosmology. They should match, they do not. The mismatch is not a small error. It is the most stunning failure of a prediction in the history of science. The vacuum energy predicted by quantum field theory is one followed by 120 zeros times larger than the dark energy we actually observe. To write that number out would take more space than this entire script. It is a discrepancy so vast it is almost meaningless. If the theoretical value were real, the repulsive force would have been so unimaginably powerful that the universe would have ripped itself to shreds in a fraction of a second after the Big Bang. Stars, planets, and life would have been impossible. The fact that we are here to measure it means something is profoundly wrong. This is not just a number being off by a factor of 10 or even a million. This is a number being off by a number so large it defies comprehension. It tells us one of two terrifying things. Either our understanding of the quantum vacuum is completely and utterly broken, or there exists some miraculous, unknown cancellation mechanism that fine-tunes this enormous energy down to the infinitesimally tiny value we see. Why is the cosmological constant so small? More pointedly, why isn't it zero, or why isn't it the colossal value that should have destroyed everything? This question cuts to the heart of whether our universe is somehow special, fine-tuned for existence, or whether we are missing a fundamental piece of physics that will rewrite the rules of both the very large and the very small. The silence of empty space is screaming a mystery we cannot yet hear. This staggering mismatch forces us to ask a deeper question. What if dark energy is not a constant at all? The cosmological constant model is beautifully simple, but nature is rarely that accommodating. Perhaps the force accelerating our universe is not a fixed feature of empty space, but something that evolves, something dynamic. Cosmologists have a name for this possibility: quintessence. Imagine the universe not as a static stage, but as a living entity breathing in and out. Quintessence would be like a fifth fundamental force field, one that permeates all of space, just like the Higgs field, but with a crucial difference. Its energy density can change over time. It can weaken or strengthen. It can even, in some theories, flip its properties entirely. To understand how we test this idea, we need to talk about a single, crucial letter, W. This is the equation of state parameter. Think of W as the personality of dark energy. It tells us the relationship between the pressure dark energy exerts and its energy density. For Einstein's cosmological constant, the value is fixed and simple: W equals -1. That specific number gives us the constant, relentless acceleration we observe. But if dark energy is quintessence, W could be different from -1. It could be greater than -1 or even less than -1, and more importantly, it could change as the universe ages. This is not a minor technicality. The value of W dictates the ultimate fate of everything. If W is exactly -1, the acceleration continues steadily, leading to a cold, dark, lonely end known as the Big Freeze. If W is greater than -1, the force of dark energy might eventually fade, allowing gravity to perhaps reassert itself in the distant future. But if W is less than -1, we face a truly apocalyptic scenario called the Big Rip. In this future, the repulsive force grows infinitely strong over time. It would first tear apart galaxy clusters, then galaxies themselves, then stars from their planetary systems. In the final moments, it would rip apart atoms, nuclei, and the very fabric of space-time. The entire universe would be shredded in a finite amount of time. So measuring W is not just an academic exercise, it is an attempt to read the final chapter of our cosmic story. Astronomers are engaged in a monumental effort to pin down this number. They use the same tools that discovered dark energy, type 1, a supernova, but now with far greater precision and in vastly larger numbers. They combine this with observations of the cosmic microwave background and the large-scale structure of the universe, mapping the distribution of millions of galaxies. Every new telescope, every sky survey is essentially trying to answer one question. Has W always been exactly -1, or is it slowly drifting? The current measurements are incredibly precise, yet tantalizingly ambiguous. They tell us W is very, very close to -1, but the data cannot yet rule out a tiny deviation. That sliver of uncertainty is where the potential for revolution lies. A definitive measurement that W is not -1 would be one of the greatest scientific discoveries of the century. It would prove that dark energy is not a static ghost in the machine, but an active, evolving component of the cosmos. It would force us to abandon the cosmological constant and open the door to entirely new physics, perhaps a unified theory that connects the quantum world with the fate of the universe itself. We are staring at a dial that controls everything, and we are still trying to see if the needle has moved. The search for W is a hunt for the future, but another conflict is tearing at the very foundation of cosmology right now. We call it the Hubble tension, and it is not a minor disagreement. It is a full-blown crisis that threatens to crack our standard model of the universe wide open. The problem is deceptively simple. How fast is the universe expanding right now? This number, known as the Hubble constant, is the single most important parameter in cosmology. It is the master clock that tells us the age of the universe and scales all cosmic distances. For decades, we believed we were homing in on a single, precise value. But modern measurements have produced two very different answers, and both sides are too confident to be wrong. The first method looks at the nearby universe. Astronomers use cosmic ladders, starting with pulsating stars called Cepheid variables in our own galaxy. These stars have a magical property. Their pulse rate is directly tied to their true brightness. By measuring how fast they pulse and how dim they appear, we can calculate their distance with stunning accuracy. We then find these same Cepheids in nearby galaxies that also host type 1, a supernova. This calibrates the supernova, turning them into our most powerful distance markers. We then look at even more distant supernova and galaxies, measuring how fast they are receding from us. The result from this local, step-by-step ladder gives us a Hubble constant of about 73 kilometers per second per megaparsec. In simpler terms, for every 3.26 million light-years a galaxy is from us, it appears to be moving away 73 kilometers per second faster. Now, the second method looks back to the infant universe. It uses the cosmic microwave background, the faint afterglow of the Big Bang, as a snapshot from when the cosmos was only 380,000 years old. By analyzing the tiny temperature fluctuations in this ancient light, the Planck satellite collaboration could infer the ingredients of the early universe, the amounts of dark matter, normal matter, and dark energy. Plugging these numbers into our standard cosmological model allows us to run the cosmic film forward, predicting what the expansion rate should be today. This early universe method gives a Hubble constant of about 67 kilometers per second per megaparsec. The numbers seem close, but in the world of precision cosmology, they are catastrophically far apart. The uncertainty in each measurement is now so small that the gap between 73 and 67 is not a blurry overlap, it is a chasm. The chance that this disagreement is a simple statistical fluke is less than 1 in a million. So we are left with a terrifying and thrilling possibility. Our measurements are flawless, but our model is broken. This tension could be a sign of new physics, a ghost in the cosmic machinery that we have not yet accounted for. Perhaps dark energy is not constant but grew stronger recently, giving the local expansion an extra kick. Maybe dark matter has properties we do not understand, interacting in strange ways. Or perhaps there is an entirely new type of neutrino or other particle that subtly altered the early universe's evolution. The Hubble tension is more than a technical puzzle. It is a direct challenge. It tells us that our beautiful, self-consistent story of the cosmos, the lambda CDM model, might have a fundamental crack. One of the pillars holding up modern cosmology is starting to groan under the strain. This chasm in our measurements forces us to confront the ultimate question. Where is all this headed? The fate of the universe hinges entirely on the unknown nature of dark energy. We are not passive passengers on this journey. The character of this mysterious force will write the final chapter, and cosmologists have outlined 3 starkly different endings. The first, and currently most likely, is the Big Freeze. Imagine a universe where dark energy behaves exactly like Einstein's cosmological constant, a steady, unchanging pressure. The acceleration continues forever at its current gentle rate. Galaxies outside our local group will eventually be pushed away so fast that their light can no longer reach us. The cosmic horizon will shrink. Over trillions upon trillions of years, star formation will cease as galaxies run out of gas. Existing stars will burn out one by one, leaving behind cold, dead remnants, black holes, neutron stars, and frozen planets. Space itself becomes unimaginably vast, cold, and empty. This is a heat death where the universe achieves a state of maximum entropy, a uniform, frigid stillness. All structure, all energy gradients, everything that makes the cosmos interesting fades away. This is the fate our current data overwhelmingly supports, but what if dark energy is not constant? The second scenario is the Big Crunch, a dramatic reversal of our current expansion. This would require dark energy to be a form of quintessence that weakens over time and eventually flips its sign, becoming attractive instead of repulsive. In this future, the acceleration would slow, stop, and then reverse. The universe would begin to contract. Galaxies would start rushing toward each other. The cosmic background temperature would rise as space is compressed. Eventually, everything would collapse back into an infernally hot, dense state, a mirror image of the Big Bang. Some theories even suggest this could lead to a cyclical universe, a big bounce where a new cosmos is born from the ashes of the old. While poetic, the evidence for this is virtually non-existent. Our observations show no sign that the acceleration is slowing down, let alone preparing to reverse. The third possibility is the most violent of all, the Big Rip. This requires dark energy to be a form of phantom energy, with an equation of state where W is less than -1. In this case, the repulsive force does not remain constant, it grows stronger over time. The acceleration becomes self-reinforcing. First, the phantom energy would overcome the gravitational glue holding galaxy clusters together. Then, individual galaxies would be torn apart. As the force intensifies, stars would be ripped from their orbits. In the final moments, roughly a finite time before the end, the repulsion would exceed the forces that bind planets, then molecules, then atoms, and finally atomic nuclei. The very fabric of spacetime itself would be shredded. The universe would end not with a whimper, but with a catastrophic, fundamental disintegration. The subtle differences between these fates come down to that single parameter, W. If W equals exactly -1, we get the Big Freeze. If W is greater than -1 and changes to become positive, we could get a big crunch. If W is less than -1, we are destined for the big rip. Our current best measurements place W incredibly close to -1, which is why the big freeze is the standard prediction. But that tiny uncertainty, that sliver of doubt, is enough to keep the other two possibilities alive in theory. So we are left with a profound realization. The ultimate destiny of every star, every planet, and every atom is currently being decided by a force we cannot detect, described by a number we cannot yet pin down with absolute certainty. We are sailing into a future written in invisible ink, and we have only just begun to decipher the first few words. But this cosmic tug of war between an invisible pull and an unseen push raises a deeper suspicion. Could dark energy and dark matter be connected? They are the twin titans of the cosmos, together making up 95% of everything. Yet in our standard model, they are perfect strangers. Dark matter clumps together through gravity, providing the scaffolding for galaxies. Dark energy is smooth, uniform, and repulsive, tearing the cosmic fabric apart. One builds, the other destroys. One is the architect of structure, the other is the agent of its eventual dissolution. It seems almost too perfect, too symmetrical to be a coincidence. What if these two shadows are whispering to each other? This idea is known as coupled dark energy. Imagine the universe is not filled with two separate, independent entities, but with a single, unified dark fluid. In this scenario, dark energy and dark matter are not distinct substances but different manifestations or phases of the same underlying unknown. They could interact, exchanging energy. Perhaps dark matter slowly decays into dark energy, feeding the acceleration over cosmic time. Or maybe dark energy can condense into dark matter under certain conditions. This is not just a wild guess. A coupling could elegantly solve several puzzles at once. For instance, it might explain the precise timing of our cosmic epoch, why dark energy only became dominant a few billion years ago, just as large-scale structure finished forming. If dark matter was converting into dark energy, its influence would have grown as the universe aged, naturally explaining the switch from a matter-dominated, slowing expansion to a dark energy-dominated, accelerating one. It could also offer a new solution to the Hubble tension. An interaction between the dark components would alter how the universe expanded in its early history, potentially shifting the predicted expansion rate derived from the cosmic microwave background to better match the rate we see in the local universe. The implications are profound. Finding evidence for such a coupling would be a revolution as significant as the discovery of dark energy itself. It would mean we have been fundamentally mischaracterizing the majority of reality. Instead of two separate mysteries, we will be facing one grand, unified enigma. The hunt is on. Astronomers are looking for subtle signatures in the way galaxies cluster across the universe and in the delicate features of the cosmic microwave background. They are searching for any deviation from the expectation that dark matter simply ignores dark energy. So far, no definitive signal has been found. The two shadows remain stubbornly separate in our data. But the possibility lingers, a tantalizing thread that, if pulled, might unravel the entire tapestry of modern cosmology and reveal a simpler, stranger truth beneath. Our cosmic history is a story of shifting gears. The expansion of the universe has not been a steady cruise. Instead, it appears to have passed through distinct eras, each governed by a different dominant force. We know of three major phases, but the unsettling possibility is that we may have missed others, hidden in the gaps of our observations. The first chapter is the most extreme, a period called cosmic inflation. In the tiniest fraction of a second after the Big Bang, the universe is thought to have undergone a burst of expansion so violent it defies all intuition. Space itself expanded faster than the speed of light, inflating a subatomic patch of reality to a size larger than our entire observable universe in less than a blink. This theory, while still unproven, elegantly explains why the cosmos appears so uniform and flat on large scales. Then, inflation ended. The energy driving that hyper-expansion decayed, filling the universe with a hot soup of particles and radiation. This began the second phase, the long era of deceleration. For billions of years, gravity was in charge. The mutual attraction of all the matter and radiation in the cosmos acted as a brake, steadily slowing the expansion down. This was the universe of structure building, where galaxies and clusters could gradually form under gravity's patient pull. Finally, roughly 5 billion years ago, a cosmic handoff occurred. As the universe expanded and diluted, the density of matter dropped. Dark energy, with its constant or near-constant energy density, became the dominant component. Its repulsive push overcame gravity's weakening grip, and the universe shifted into the third and current phase, acceleration. We are now living in this dark energy-dominated epoch where the stretching of space is speeding up. But this tidy three-act play may be incomplete. Could there have been other, subtler transitions we have not yet detected? The Hubble tension, that stubborn disagreement about the current expansion rate, is a glaring clue that our timeline might be wrong. Perhaps dark energy's strength is not perfectly constant. Maybe it experienced a recent hardening, a slight increase in its repulsive power that gave the local universe an extra jolt, explaining the faster expansion rate measured from nearby supernova. Conversely, maybe it softened for a period, slowing down slightly before resuming its push. These are not wild speculations, but serious models cosmologists are testing. Finding evidence for an unknown expansion phase would rewrite the cosmic biography. It would mean the universe's history is more complex and dynamic than our simple model suggests, with hidden chapters still waiting to be read in the faint light of the distant cosmos. This shifting history of our universe leads us to a more tangible, yet equally elusive question. If dark energy is a real component of the cosmos, does it have mass? Does it come in particles? We are used to thinking of the universe's contents in terms of stuff, from atoms to photons to the hypothesized particles of dark matter. But dark energy resists this categorization with every fiber of its being. Consider the simplest idea, the cosmological constant. In this view, dark energy is not a substance at all, but a property of empty space itself, a fixed energy density of the vacuum. You cannot bottle a property, you cannot find a particle for it because it is not made of things. It is simply the cost of having space. It would be like asking what particle carries the curvature of spacetime described by general relativity. There isn't one, it is geometry. So if dark energy is Einstein's constant, then the answer is a definitive no. It has no mass and no particles. It is the stage, not an actor upon it. But what if the stage itself is alive? If dark energy is a dynamic field like quintessence, then the rules change dramatically. In physics, every fundamental field has an associated particle. The electromagnetic field has photons, the gravitational field, in theory, has gravitons, the Higgs field has the Higgs boson, so a quintessence field should have its own particle, often whimsically called a quintessaron. What would such a particle be like? To produce the smooth, repulsive effect we observe across billions of light years, this particle would likely be incredibly light, potentially even massless, and it must interact with normal matter with unimaginable weakness. Its effects are only noticeable on the grandest scales because it is so feeble locally. Trying to detect a single quintessaron particle in a laboratory would be like trying to hear a single snowflake land in the middle of a roaring hurricane. Its signal would be drowned out by every other process in the universe. This weakness is why we have not found it and may never directly detect it with particle colliders. The hunt, therefore, turns to indirect cosmic evidence. Some intriguing theories even propose links between this shadowy sector and particles we already know, like neutrinos. Neutrinos are ghostly, nearly massless particles that flood the universe, barely interacting with anything. Could dark energy be connected to them, perhaps through some exotic fifth force, a new interaction that only affects neutrinos and the quintessence field, subtly changing how they behave over cosmic distances? If we could measure the properties of neutrinos from the early universe with extreme precision, we might see the imprint of this conversation with dark energy. The very idea that the fate of the cosmos could be tied to the behavior of the universe's most elusive known particle is a stunning reminder of how interconnected the mysteries are. So we are left with a profound duality. Dark energy could be a static feature of the void, massless and particle-free, a fundamental rule of reality. Or it could be a whispering field with its own ethereal particle, so light and weakly coupled that it hides in plain sight, shaping the universe from the shadows. Our answer determines whether we are searching for a new law of physics or for a new form of matter so strange it defies all our usual definitions. This middle chapter of cosmic history is often overlooked, yet it holds the key to our present reality. For billions of years after the frenzy of inflation and the hot Big Bang, the universe was in a state of graceful slowdown. This was the deceleration phase, a long, patient era where gravity reigned supreme. Picture a ball thrown high into the air. At the peak of its arc, it appears to hang for a moment before surrendering to the pull of Earth. The expanding universe was like that ball, climbing against its own gravity. Every galaxy, every particle of matter and dark matter was pulling on every other, acting as a cosmic brake. This relentless tug of war was slowing the expansion down. During this time, the universe was a master builder. That slowing was essential. It gave gravity the time it needed to work. Tiny density fluctuations from the early universe, seeds planted during inflation, could slowly, over eons, gather more and more material. Gas could cool and condense. The first stars ignited, then galaxies swirled together, and clusters of galaxies formed the largest structures in the cosmos. All of this magnificent architecture, the web of light we see today, was constructed during this era of deceleration. It was the universe's golden age of formation. But this could not last forever. The very expansion that gravity was trying to slow was also diluting the source of gravity's strength. As space stretched, the density of matter, both normal and dark, was steadily decreasing. Think of it like a rubber band being stretched. The particles on it move farther apart and their collective pull weakens. Dark energy, however, presents a profound puzzle. In the simplest model, as a cosmological constant, its energy density does not dilute. It remains constant, a fixed amount of repulsive energy in every cubic centimeter of space forever. So as the universe expanded and matter's density dropped, there came a critical tipping point. Roughly 5 billion years ago, the density of matter finally fell below the constant density of dark energy. It was a silent, invisible crossover. The repulsive push of the vacuum, which had been present all along but overshadowed by gravity's stronger grip, finally became the dominant force in the cosmos. The brake was released and the accelerator was pressed. The universe transitioned from deceleration to the acceleration we live with today. Pinpointing the exact moment of this transition is one of the most important goals in cosmology. It is not just about marking a date on the cosmic calendar. That crossover point is exquisitely sensitive to the nature of dark energy itself. If dark energy is a simple constant, the transition happened at a very specific time, leaving a particular signature in how galaxies are distributed across the universe. But if dark energy is dynamic, if its strength has waxed or waned, then the transition could have happened earlier or later, or perhaps even in a more gradual, blurred manner. Astronomers are therefore turning into cosmic archaeologists, digging through layers of time. They use distant supernovae as markers, but also chart the growth of galaxy clusters across billions of years. By measuring how fast large-scale structure formed at different epochs, they can sense when gravity's grip began to loosen. Did galaxy cluster growth slow down abruptly 5 billion years ago, or was it a more gradual tapering off? The answer writes the biography of dark energy. Finding that precise transition is like discovering the exact moment in a person's life when their destiny changed course. It tells us whether the force shaping our future has always been the same, or if it has a history of its own, a history we are only now beginning to read in the fading light of ancient stars. The precise moment of that cosmic handoff depends on a quiet assumption, one so fundamental we rarely question it. We assume the universe is uniform, the same in all directions. This is the bedrock of cosmology, known as the cosmological principle. But what if this principle is wrong? Our 10th question asks, is the expansion truly isotropic? Is the universe stretching evenly in every direction, or are we seeing hints of a hidden cosmic axis, a preferred direction in the void? The implications are staggering. If the expansion has a direction, it means our place in the cosmos is not average, and our entire model of the universe could be built on a flawed foundation. The search for this anisotropy, this lack of uniformity, has led scientists to some of the most controversial observations in modern astronomy. One of the earliest and strangest clues came from the cosmic microwave background itself, that ancient afterglow of the Big Bang. When scientists created a detailed map of its temperature fluctuations, they expected a random, symmetric pattern like static on an old television screen. Instead, some analyses claim to find odd alignments on the largest scales. Certain hot and cold spots seemed to line up in a way that defied simple chance. Skeptical researchers half-jokingly called this alignment the axis of evil, because if real, it would undermine the Standard Model's most basic assumption. While later studies have questioned the statistical significance of this particular anomaly, the name stuck, a ghost in the data that refuses to be fully exorcised. More recently, another potential crack has appeared, this time involving distant quasars. Quasars are incredibly bright cores of active galaxies powered by supermassive black holes. Light from these beacons travels billions of light years to reach us. Along the way, its electromagnetic waves can become polarized, meaning they vibrate in a preferred plane. In 2011, a team of astronomers announced a shocking finding. They claimed the polarization axes of light from hundreds of quasars, spread across vast swaths of the sky, were not randomly oriented as expected. Instead, they appeared to align with each other over distances that should be causally disconnected. Regions of space that have never been in contact since the beginning of time. This was not just odd, it was seemingly impossible under the Standard Model. If the universe is isotropic, such a coordinated alignment across billions of light years makes no sense. It would suggest a universal directionality imprinted on the fabric of space itself, perhaps a relic from the epoch of inflation that never smoothed out. Then there are the mysterious bulk flows. We measure the expansion of the universe by assuming that, on the largest scales, galaxies are simply carried apart by the stretching of space. Their individual, peculiar motions should cancel out, but observations suggest something else might be happening. Enormous clusters of galaxies containing thousands of members appear to be streaming together in a coherent direction at speeds far greater than our models predict. It is as if a vast river of matter, hundreds of millions of light years across, is flowing in a specific direction, tugged by a gravitational pull that our maps of visible and dark matter cannot account for. This could be a sign of an immense, unseen structure beyond our observable horizon, a cosmic continent whose gravity is pulling us. Or, more radically, it could indicate that the expansion rate is not the same in all directions. Perhaps space is stretching faster in one part of the sky and slower in another, creating a current that sweeps galaxies along. The scientific community remains deeply divided on these anomalies. Many argue they are statistical flukes, artifacts of complex data analysis, or caused by more mundane astrophysical effects we do not yet fully understand. The alignment of quasar polarizations, for instance, is hotly debated, with other teams failing to reproduce the result with newer data. But the possibility, however slim, refuses to die. If just one of these hints were confirmed, the consequences would be revolutionary. A preferred direction would mean the universe has a north and south, a cosmic orientation we could point to. It would invalidate the cosmological principle and force us to completely rethink our origin story. We would have to ask, are we in a special place near the center of some vast cosmic unevenness, or is the entire universe fundamentally lopsided, a relic of a chaotic birth? For now, these observations remain ghosts at the edge of our vision, whispers of a deeper truth or mere illusions in the data. Their very existence, however, is a vital reminder that our most cherished assumptions about the cosmos are not laws, but hypotheses waiting to be broken. These whispers of a lopsided cosmos force us to question the very stage upon which the drama plays out. What if our reality is not the whole story? This leads us to an even more radical question, one that sounds like science fiction but is taken deadly seriously by theoretical physicists. Does gravity leak out of our universe? To understand this, we must step beyond the familiar three dimensions of space and one of time. In our daily lives, we move forward and back, left and right, up and down. That is it, but for nearly a century, physicists have theorized that extra, hidden dimensions could be curled up at scales so tiny we could never perceive them directly. Like a garden hose that looks like a one-dimensional line from far away, but is actually a two-dimensional surface when viewed up close. These extra dimensions were originally proposed to unify the fundamental forces, but a groundbreaking idea from the late 1990s, known as the Randall-Sundrum model, gave them a terrifying and elegant new purpose. It suggested that our entire three-dimensional universe, with all its stars, galaxies, and us, could be a membrane, or brain for short, floating within a higher dimensional space called the bulk. In this picture, all the forces and particles we know, like light and matter, are stuck to our brain. They cannot leave, but gravity is different. Gravity, the warping of space-time itself, might not be confined. It could be the only force that can seep out or leak into the extra dimensions of the bulk. Think of our universe as a sheet of paper floating in a vast room. Everything we see and touch exists on that paper, but if you spill water on the paper, some of it soaks through to the air below. In this analogy, gravity is the water. Now consider what this leakage would mean over cosmic distances. On Earth or within our solar system, gravity appears strong because the extra dimensions are curled up incredibly small. The leakage is negligible, like a tiny, almost imperceptible amount of water evaporating from a full glass. But on the scale of the universe across billions of light years, that slight seepage could add up. The gravitational pull between two distant galaxy clusters would be subtly weaker than our standard laws predict, because some of their attractive force is bleeding away into dimensions we cannot see. From our perspective, trapped on our three-dimensional brain, this would look exactly like a repulsive force pushing things apart. The math is startling. A weakening of gravity over vast distances caused by its escape into a higher dimension could perfectly mimic the observed effects of dark energy. In this view, the acceleration of the universe is not driven by a mysterious new energy. It is an illusion, a cosmic mirage created by our incomplete understanding of gravity's true nature. We are not seeing a push, we are witnessing a pull that is slowly fading because it is leaking into the walls of reality. The implications are profound. If true, it would mean that dark energy does not exist as a substance or a field. It is a signpost pointing to a larger, hidden architecture of reality. The greatest mystery in cosmology would be solved not by discovering a new particle, but by realizing we live in a higher dimensional space we can never directly access. Of course, this is an extraordinary claim, and it requires extraordinary evidence. Scientists are searching for subtle signatures. If gravity behaves differently on galactic or intergalactic scales than it does in our solar system, that could be a clue. Some experiments are looking for deviations from Newton's and Einstein's laws in the motions of stars within galaxies or in the lensing of light around massive clusters. So far, no definitive proof of extra dimensions or gravitational leakage has been found. The standard model with its separate dark energy still fits the data well. But the possibility remains a tantalizing escape hatch from our current crisis. A reminder that the answer to the universe's greatest mystery might not be hidden in the darkness between stars, but in the unseen folds of space itself. Gravity is the oldest force we have ever known, the silent architect of the cosmos. Yet its own story might be incomplete. If gravity can leak into unseen dimensions, could it also simply behave differently than we think on the grandest stages? This leads to a radical and elegant alternative. Perhaps dark energy does not exist at all. Our 12th question asks, is the accelerating expansion actually a sign that gravity itself needs an update? The idea is breathtaking in its simplicity. Instead of inventing a mysterious new energy that makes up most of the universe, we could be witnessing the slow failure of Einstein's theory of general relativity on the scale of the cosmos itself. For over a century, general relativity has been our unshakable guide to the large-scale universe. It describes gravity not as a force, but as the curvature of space-time caused by matter and energy. It predicted black holes, gravitational lensing, and the expansion of the universe with stunning accuracy. But every theory has its limits. Just as Newton's laws break down at near light speeds or in strong gravitational fields, perhaps Einstein's masterpiece also has a domain of failure, a scale so vast that its equations need a subtle tweak. This pursuit is known as modified gravity. One of the most famous and controversial branches is called MOND, or modified Newtonian dynamics, originally proposed to explain the rotation of galaxies without dark matter. Some of its extensions also attempt to tackle cosmic acceleration. The core idea is that the laws of gravity change when the gravitational pull becomes incredibly weak, as it is in the outskirts of galaxies or in the vast voids between galaxy clusters. In these extreme low acceleration environments, gravity might become slightly stronger than standard theory predicts. This extra pull could, in certain cosmological models, mimic the effect of a repulsive dark energy, driving an apparent acceleration. But for the cosmic acceleration specifically, a more sophisticated class of theories has emerged, known as F of R gravity. Here, the R stands for the Ricci scalar, a mathematical term in Einstein's equations that describes the curvature of spacetime. In standard general relativity, this term is simple and linear, but in F of R gravity, scientists allow it to become a more complex function. Think of it like this. General relativity describes spacetime as a perfectly elastic sheet. Push on it and it bends predictably. F of R gravity suggests that on the largest scales, the sheet has a different elasticity. It might resist bending in a new way or spring back with a subtle extra force that we, from our limited perspective, interpret as a repulsive push. By carefully choosing this mathematical function, theorists can make the modified equations produce an accelerating expansion without inserting a single drop of dark energy. The universe accelerates because gravity's rules have changed, not because a new force is acting. The appeal is immense. It removes the need for a bizarre, dominant component we cannot explain. It returns gravity to the center stage as the sole sculptor of cosmic destiny. But the challenge is even greater. Modified gravity theories must pass an obstacle course of observational tests, and many stumble. First, they must perfectly reproduce all the successes of general relativity within our solar system. We have exquisitely precise data from the orbit of Mercury, the bending of starlight, and signals from passing spacecraft. Any modification cannot disturb these confirmed predictions. Second, and more critically, they must match the detailed observations of the large-scale universe. They need to explain the specific pattern of galaxy clustering, the precise features of the cosmic microwave background, and the observed behavior of light bending around massive clusters, a phenomenon called gravitational lensing. This is where the theories often struggle. While they can be tuned to produce an overall acceleration, matching the fine details of how structure forms and evolves across cosmic time is extraordinarily difficult. The standard model with dark matter and a cosmological constant for all its mysteries does this job with remarkable precision. It acts like a key that fits a very complex lock. Crafting a modified gravity theory that fits that same lock without using the dark energy key has so far proven to be a monumental task. Furthermore, these theories often introduce new problems of their own. Many of our models predict the existence of exotic, ghost-like particles or lead to instabilities in the fabric of space-time. Others might work for the expansion history but fail to explain the separate evidence for dark matter from galaxy rotations and cluster collisions. The hunt, therefore, is for a consistent, complete theory that can do everything our standard model does, but without its two biggest unknowns. As of now, no such theory has achieved widespread acceptance. The data continues to favor the existence of two separate dark components, yet the pursuit remains vital. It is a necessary pressure test for our foundational ideas. Every attempt to modify gravity, even those that ultimately fail, teaches us something new about the resilience of Einstein's vision and the strange clues the universe is giving us. We are left with a cosmic trial. Is the universe filled with a mysterious, repulsive something, or are we watching gravity perform a dance whose final steps we have not yet learned? The answer will redefine our most basic understanding of reality. This cosmic trial between a new force and a modified law leaves us with a staggering coincidence. We exist at a moment in cosmic history that seems statistically impossible. For the vast majority of the universe's 13.8 billion-year lifespan, the densities of dark matter and dark energy were wildly different. In the early eons, dark matter's density was astronomically higher, dominating the cosmos and driving its deceleration. In the far, far future, dark energy's constant density will be all that remains as matter dilutes away to virtually nothing, leading to an eternal, empty acceleration. The transition between these two eras, the moment when their densities become roughly comparable, is a fleeting blink in cosmic time, and we are here, alive and observing, right in the middle of that blink. This is the profound why now problem, also called the coincidence problem. The numbers are startling. Today, the energy density of dark matter and the energy density of dark energy are within a single order of magnitude of each other. That means one is only about 3 times larger than the other. Given the universe's immense age and the fact that these densities change at drastically different rates, the odds of us catching them at such a similar level seem vanishingly small. It is as if you walked into a room just as a single, specific grain of sand was falling through an hourglass that had been running for billions of years. This is not just a curious fact, it is a direct challenge to the simplest cosmological constant model. If dark energy is truly a constant and dark matter simply dilutes as the universe expands, then this moment of near equality is a one-time event, a fleeting coincidence with no deeper meaning. We just got astronomically lucky. Many scientists find this explanation deeply unsatisfying. In physics, a staggering coincidence is often a clue, a sign that we are missing a fundamental connection. The why now problem strongly suggests that dark matter and dark energy are not independent strangers in the cosmos. Their densities are comparable now because they are linked, two sides of the same dark coin. This thinking fuels the theories of coupled dark energy we touched on earlier. If the two dark components interact, exchanging energy, then their evolution is tied together. Their densities could be designed through the physics of their interaction to cross paths and remain comparable for a long period, perhaps even for the entire lifetime of stars and galaxies. In such a model, our existence during this era is not a freak accident. It is a necessity, a universe where structure forms, where galaxies and stars and planets have time to arise, may only be possible during this extended window when the densities are balanced. Too much dark matter too early, and structure forms too quickly and violently. Too much dark energy too early, and the universe accelerates before anything can clump together. We find ourselves in the cosmic sweet spot because it is the only spot where observers like us could ever exist. This idea, known as the anthropic principle, is controversial but impossible to ignore in this context. It shifts the question from why are the densities equal now to what physical laws allow for a long period of near equality where life can emerge. The why now problem, therefore, is more than a puzzle about timing. It is a beacon pointing toward a deeper, unified theory of the dark sector. It tells us that the greatest mysteries of the cosmos are likely not separate, but intimately intertwined, and that our moment in the light is a direct message from the darkness. The smooth cosmic history we just traced hides a violent, pivotal moment at its very beginning. That moment was the end of inflation, and it is absolutely critical to everything that came after, including the stage now set for dark energy. Inflation was not a gentle expansion. It was a runaway stretching of space driven by a field with an enormous vacuum energy density, far beyond anything dark energy represents today. For this hyper-expansion to give way to the orderly, decelerating universe of the Big Bang, it had to stop, and the way it stopped determined the character of our entire cosmos. The central mystery is how all that incredible vacuum energy, which was inflating space itself, was converted into the hot soup of particles that filled the early universe. Cosmologists call this process reheating, though nothing was hot before it. It was more like the universe's first and greatest firestorm. Think of the inflating universe as a ball perched high on a hill. This position represents the high energy state of the inflation field. As long as the ball stays there, inflation continues, stretching space exponentially. But this state is unstable. At some point, the ball must roll down the hill. When it does, the enormous potential energy stored in its high position is released. In the cosmic analogy, that energy does not just vanish. As the inflation field tumbles down its energy slope, it begins to oscillate rapidly at the bottom. These violent oscillations act like a colossal pump, transferring energy out of the field and into the creation of every known particle and force. It is as if the energy of the vacuum itself was shaken furiously until it shattered into quarks, electrons, photons, everything. This was the moment of reheating, when the cold, empty, inflated universe was flooded with seething heat and matter, marking the true beginning of the hot Big Bang. But the transition had to be just right. If the energy transfer was too efficient or too violent, it could have created catastrophic inhomogeneities, vast over dense regions that would have collapsed into primordial black holes, or left behind dangerous relics that would dominate the cosmos today. If it was too inefficient, the universe would have been left cold and empty, with no particles to form stars or galaxies. The mechanism had to be exquisitely tuned to produce the remarkably smooth, flat universe we observe. That smoothness is inflation's other great gift, and its end had to preserve it. During its exponential growth, inflation stretched any initial irregularities in space-time to scales far larger than our observable universe, ironing the cosmos flat and uniform. But the reheating process itself could have introduced new wrinkles. The decay of the inflation field had to be coherent and widespread, like a perfectly synchronized clock ticking across the entire universe at once, ensuring that the transition to the hot phase happened at nearly the same moment and temperature everywhere. Any significant lag between one region and another would have left imprints in the cosmic microwave background that we simply do not see. The fact that we observe such stunning large-scale uniformity tells us that the end of inflation was not a chaotic, splintered event, but a remarkably coordinated phase change for all of reality. Understanding this transition is not just about ancient history. It sets the initial conditions for the entire expansion story that follows, including the eventual rise of dark energy. The density of matter and radiation, the specific pattern of tiny seeds that grew into galaxies, even the overall geometry of space, were all locked in during this crucial pivot. The vacuum energy of inflation vanished, transformed into the stuff of the universe. Today, we face a different vacuum energy, dark energy, which is not transforming but persisting. The contrast is profound. One vacuum energy ended explosively to create our world. The other lingers quietly, perhaps destined to dissolve it. The end of inflation was the first and most dramatic handoff in cosmic history, a model for how the universe can shift gears. Now we must ask if the current handoff to dark energy domination will have a final, silent act of its own. But the smoothness of that ancient transition masks a startling texture in today's cosmos. Our universe is not a uniform soup. It is a vast cosmic web, a tapestry woven from brilliant clusters of galaxies, connecting filaments of dark matter, and immense, nearly empty voids stretching hundreds of millions of light years across. This structure is not just scenery. It may be actively distorting our view of the expansion itself. Here is the crucial question: are the voids expanding faster than the clusters? The answer could unravel the Hubble tension. According to Einstein's general relativity, gravity is the curvature of spacetime caused by mass and energy. In a region teeming with matter, like a galaxy cluster, the gravitational pull is strong. This creates a deep well in the fabric of space. Within that well, the local expansion of the universe is suppressed. The galaxies are bound together tightly, resisting the overall stretching of the cosmos. They have their own peculiar motions, but the background expansion is slowed by their mutual attraction. Now step into a void. These are the deserts of the universe, regions where the density of matter is only a tenth of the cosmic average or even less. Here, gravity's grip is feeble. There is very little mass to curve spacetime to create a resisting well. In these emptiness, the repulsive push of dark energy meets almost no opposition. Think of the universe as a stretching rubber sheet with weights placed upon it. The weights, the galaxy clusters, create dimples. The rubber around the weights stretches easily, but the dimples themselves deform more slowly. The voids are the flat, weightless regions of the sheet, free to expand at the maximum rate allowed by dark energy. This means the expansion rate is not a single, universal number you can point to. It is a local variable depending on where you measure it. If you take your yardstick and your supernova and measure the expansion from within a deep void, you will get a higher value for the Hubble constant. If you measure it from within a rich cluster, you will get a lower value. We are not floating in a perfectly average place. Our Milky Way resides in a small galaxy group, which is part of the Laniakea supercluster, a massive filament of structure. We are in the suburbs of the cosmic web, not deep in a void nor at the heart of a dense cluster, but our local measurements rely on objects that are themselves embedded in this complex landscape. Could it be that the local measurements, which use Cepheid stars and supernova in relatively nearby galaxies, are accidentally sampling a region that is slightly more underdense than the cosmic average? Perhaps our galactic neighborhood is part of a local void, a bubble of lower density, causing us to measure an expansion rate that is a few percent too high. Conversely, the early universe measurement from the cosmic microwave background gives a truly global average, a snapshot of the universe when it was smooth and homogeneous before these vast structures had fully formed. This method naturally yields the average expansion rate for the entire cosmos. The discrepancy, then, would not be a sign of new physics but a cosmic illusion. It would be a measurement error born from our specific, non-average location in a lumpy universe. Scientists call this the Hubble bubble hypothesis. The challenge is quantifying it. Is our local void large enough and empty enough to produce the entire 5 to 6% difference we see in the Hubble constant? Current mapping of our local universe suggests we are in a moderately underdense region, but perhaps not extreme enough to fully explain the tension. Yet the possibility remains compelling. It forces us to confront a profound humility. We may not be at the center of the universe, but we are also not in a perfectly representative place. Our entire view of cosmic destiny is filtered through the specific gravitational landscape we inhabit. The expansion rate we measure is not just a number about the universe. It is a number about our universe from our particular address within it. That cosmic landscape, so varied and complex today, presents us with a paradox when we look back to the very beginning. The infant universe was stunningly, impossibly smooth. This is the horizon problem, one of the most profound puzzles that ever faced cosmology, and its solution may whisper secrets about the force shaping our future. When we examine the cosmic microwave background, the oldest light in the universe, we see a near-perfect uniformity. The temperature of that primordial glow is the same in every direction to about 1 part in 100,000. This seems natural until you realize the shocking implication. Regions of the sky on opposite sides of the universe were never in contact. Light, the fastest thing in existence, has not had enough time since the Big Bang to travel between them. They were causally disconnected, forever beyond each other's influence. How then did they agree on the exact same temperature? It is as if two orchestras on different continents with no communication began playing the same symphony at the exact same moment, down to the last note. Without a mechanism to connect them, such perfect coordination is impossible. This was the crisis that inflation elegantly resolved. The theory proposes that in the first sliver of a second, the universe underwent a burst of expansion so unimaginably fast that a tiny, subatomic patch of space, which was in thermal equilibrium and thus uniform, was stretched to a size larger than our entire observable universe. All the regions we see today were once crammed into that infinitesimal connected dot. They were in causal contact, they reached the same temperature, and then inflation blew them apart to distances that make them seem disconnected. It ironed out any wrinkles and set the stage for the smooth cosmos we observe. But here is the crucial link to our current mystery. What powered that incredible hyper-expansion? It was a field often called the inflaton, with an enormous vacuum energy density. This energy created a powerful repulsive gravity, stretching spacetime exponentially. Sound familiar? The mechanism that drove inflation, a form of vacuum energy causing rapid, repulsive expansion, bears a haunting mathematical resemblance to the mechanism of dark energy. One is a colossal, short-lived burst, the other is a feeble, persistent whisper. They could be different manifestations of the same underlying physics. Perhaps dark energy is the ghost of inflation, a leftover remnant of that initial field that never completely decayed. Or maybe the inflaton field transformed into the quintessence field we experience today. Understanding the precise physics of inflation, the exact nature of that primordial vacuum energy, is not just about ancient history. It is a direct probe into the family of forces that includes the dark energy currently accelerating our universe. If we can decipher the rules of that first, violent expansion, we might finally understand the rules of this slow, silent one that governs our fate. The horizon problem, therefore, is more than a solved puzzle. It is a bridge across time, connecting the first moment to the last, asking if the same unknown hand has been steering the cosmos all along. The smoothness of the infant cosmos gave way to a universe of spectacular structure, but that growth did not happen in a vacuum. As galaxies and clusters formed, they were engaged in a silent, cosmic tug of war. On one side, gravity tirelessly pulled matter together. On the other, the relentless push of dark energy worked to pull it all apart. This battle defines our 17th question: how does dark energy affect galaxy formation? The answer reveals a subtle but profound influence that may have shaped the very architecture we see today. In the early universe, when matter was dense and dark energy's influence was negligible, gravity had the upper hand. Tiny ripples from the Big Bang grew steadily, drawing in gas and dark matter, forging the first stars and galaxies. This was gravity's golden age, but as the cosmos expanded and diluted, dark energy's constant presence began to tip the scales. Its repulsive effect acts as a kind of cosmic friction, a gentle but persistent resistance against gravity's pull. Imagine trying to build a sandcastle as the tide comes in. Each wave does not destroy your work instantly, but it constantly washes away loose grains, making it harder to pile the sand higher. Dark energy is like that incoming tide on a cosmic scale. It does not prevent galaxy formation outright, but it makes it more difficult for new, large structures to collapse, especially the most massive galaxy clusters. Theoretically, we expect dark energy to have put a brake on the growth of the largest structures in the universe sometime within the last 5 billion years. Before that epoch, clusters grew rapidly. After dark energy became dominant, their growth should have slowed, even stalled. The universe's largest buildings stopped adding new floors. The quest now is to find observational proof of this slowdown. How do you measure the growth of something as vast as a galaxy cluster across billions of years? Astronomers become cosmic demographers. They use powerful telescopes to conduct massive surveys, mapping the precise three-dimensional positions of millions of galaxies across different epochs of cosmic time. By analyzing this map, they can measure a property called clustering strength, essentially how tightly packed together galaxies are on enormous scales. The theory makes a clear prediction. If dark energy is actively suppressing growth, then the clustering of galaxies should be weaker in the recent, dark energy-dominated universe than it was in the distant past. It is a staggeringly difficult measurement, requiring immense precision to distinguish the subtle signal from the cosmic noise. Early results from surveys are tantalizing. They suggest the growth of structure is indeed slowing down, just as the dark energy model predicts. But the evidence is not yet ironclad. Other factors, like the complex physics of galaxy formation itself, can mimic these signals. The hunt continues with ever larger telescopes and deeper surveys, each one a snapshot in time, allowing us to watch the cosmic tide rise in slow motion. This influence is not just about the past, it writes the future of the cosmic web. In a universe dominated by a cosmological constant, the formation of new, giant galaxy clusters is effectively over. The largest structures we see today are the largest there will ever be. The cosmic web will slowly freeze in place, then, over trillions of years, begin to unravel as the accelerating expansion tears galaxies apart. Dark energy did not just change the speed of the universe, it changed its destiny from a place of endless building to one of eventual, quiet dissolution. The story of galaxy formation is no longer solely a tale of gravity's triumph, but a delicate balance between two fundamental forces, one that builds our world and one that will, in time, take it apart. This delicate balance between construction and dissolution feels less like a cosmic accident and more like a precisely set dial. The universe's expansion and the dark energy driving it appears to be fine-tuned to an almost impossible degree. If any of the fundamental constants were off by even a hair, our reality would be sterile, empty, or never have existed at all. This is the fine-tuning problem, and it asks a deeply unsettling question. Why is our universe so perfectly calibrated for complexity? Consider the density of dark energy. The value we measure is absurdly small, but crucially, it is not zero. Its precise value sits in a breathtakingly narrow window that allows for everything we see. If dark energy were even slightly stronger by a factor of just a few hundred, its repulsive push would have overwhelmed gravity in the universe's infancy. No galaxies, no stars, no planets would have ever formed. The cosmos would have been ripped apart into a featureless, accelerating void before any structure could coalesce. The universe would be a dark, empty, and lonely place. Now consider the opposite. If dark energy were slightly weaker, or worse, if it were negative, acting as an attractive force, then gravity's grip would have been even more dominant. The universe would have decelerated rapidly and collapsed back in on itself in a catastrophic big crunch long before stars had time to forge the heavy elements necessary for life. The cosmic story would have been brutally short. The window for a universe that lasts billions of years and builds galaxies is incredibly, vanishingly small. And dark energy's density falls right in the middle of that sliver, but the fine-tuning does not stop there. The initial expansion rate from the Big Bang, the amount of ordinary matter, the strength of gravity itself, all seem perfectly balanced on a knife's edge. Alter any one of these values by a minuscule fraction, and the outcome is a dead universe. It is as if someone took a cosmic control panel with 100 dials, each one representing a fundamental constant, and set every single one to an exact, specific value that allows for galaxies, stars, planets, and ultimately, observers like us to arise. This precision is so extreme that many physicists and philosophers find it deeply troubling. It suggests one of several profound possibilities, each more mind-bending than the last. The first is the anthropic principle we touched on earlier. In a vast multiverse where countless universes bubble into existence with different random constants, we inevitably find ourselves in one of the rare, fine-tuned universes capable of supporting life. We are not here because the universe was designed for us. We are here because only in such a universe could we ever ask the question. The second possibility is that there is a deeper, unifying theory that we have not yet discovered, one that logically dictates the values of all constants, leaving no room for randomness. The constants are what they are because the mathematics of reality demands it. The third and most radical is the suggestion of some form of cosmic design, though this lies outside the realm of testable science. For scientists, the fine-tuning problem is not a reason to stop looking for answers, but the ultimate motivation. That staggering precision is a clue written into the fabric of reality itself, a signpost pointing toward a deeper layer of physics where these seemingly arbitrary numbers are not arbitrary at all. The mystery of dark energy is therefore wrapped in an even greater mystery. We are not just searching for what it is, but for why it is exactly as it is in a universe that seems inexplicably tailored for our existence. That staggering fine-tuning, the sense of a cosmos perfectly balanced for life, rests entirely on a single, monumental assumption. We assume that when we measure the expansion of the universe, we are seeing a smooth, global property of space itself. But what if the very lumpiness of the cosmos is playing a trick on us? This leads to a radical, controversial idea. Could dark energy be nothing more than a cosmic mirage, an illusion born from our own flawed perspective? This is the heart of the back-reaction hypothesis, a theory that challenges the very methodology of modern cosmology. To understand it, we need to step away from the smooth equations and confront the true, gritty texture of reality. Our universe is not a uniform fluid. It is a wild landscape of extreme contrasts. Dense galaxy clusters containing trillions of stars are connected by delicate filaments of dark matter, all surrounding cavernous voids hundreds of millions of light years across, regions that are nearly devoid of any matter at all. This is not a minor detail. It is the dominant architectural feature of everything we see. In our standard model, we treat this lumpy universe as if it were a smooth average. We take the complex, clumpy distribution of matter and dark matter, we mathematically smear it out into a uniform soup, and we plug that average density into Einstein's equations. Those equations then give us a smooth, ever-expanding space-time. It is a brilliant and successful approximation, but it is still an approximation. The back-reaction theory asks a dangerous question. What if, by smoothing out the universe, we are throwing away the most important part of the story? The theory suggests that the gravitational effects of these immense inhomogeneities, these clusters and voids, do not simply average out to zero. Instead, they create a collective back-reaction on the expansion of space itself. Think of it like this. Imagine you're trying to measure the average depth of a wildly choppy ocean during a storm. If you simply take the height of the waves and the depth of the troughs and calculate a mathematical average, you might get a certain number. But that number tells you nothing about the powerful currents and forces churning beneath the surface, forces that are actively changing the shape of the ocean itself. In the cosmic analogy, the dense clusters are like the deep troughs, where gravity is strong and expansion is heavily suppressed. The vast voids are like the towering waves, where gravity is weak and expansion runs wild. When you try to stitch these wildly different regions together into a single, smooth expansion rate for the entire universe, you might get a distorted answer. Proponents of back-reaction argue that this stitching process is mathematically flawed. They propose that the rapid expansion of the giant voids over time begins to dominate the overall behavior of the cosmos. As voids grow and merge, they take up more and more volume. The expansion rate we measure from within our lumpy environment, which is influenced by these runaway voids, could therefore appear to be accelerating, even if the underlying equations, when applied correctly to the unsmoothed universe, do not contain any dark energy at all. In this view, the acceleration is not driven by a mysterious repulsive force. It is a geometric illusion, a side effect of the universe's own complex, clumpy structure. We are not seeing a push, we are misreading the gravitational landscape. The appeal is immense. It would eliminate the need for dark energy, the fine-tuning problem, and potentially even the Hubble tension, all in one elegant stroke. It suggests we have been solving the wrong problem with an exotic solution, when the answer was hidden in the plain sight of cosmic structure all along. But can this idea survive contact with data? The challenge is ferocious. To prove back-reaction, theorists must build a new, non-averaged model of cosmic expansion that starts from a realistic, lumpy universe, and then show that it naturally produces an apparent acceleration matching our supernova observations, the cosmic microwave background, and the large-scale structure, all without adding any dark energy. This is a monumental computational and theoretical task. So far, while intriguing effects have been shown in simplified models, no one has produced a complete, working alternative to the standard model that convincingly reproduces the full suite of cosmological data. Most cosmologists remain skeptical, arguing that detailed calculations show the back-reaction effect is far too small to account for the observed acceleration. They believe the smooth approximation, while not perfect, is fundamentally sound. Yet, the theory persists as a vital counter-narrative. It is a necessary rebellion, a reminder that our maps of the cosmos are just that, maps. And sometimes, the most profound mysteries are not out there in the darkness, but in the assumptions we make when we try to draw the lines. The very idea of a negative mass seems to violate every intuition physics has ever given us. Mass is the stuff of things, the measure of an object's resistance to being pushed, its source of gravitational attraction. It is positive, tangible, heavy. But to untangle the deepest knots of cosmic acceleration, some theorists are willing to venture into the logically bizarre. They ask, could dark energy be a form of matter with a negative inertial mass? This is not merely a mathematical curiosity. It is a concept that, if real, would rewrite the foundational laws of reality. In our everyday experience, mass has two inseparable faces. The first is inertial mass. This is the m in Newton's famous equation. Force equals mass times acceleration. It quantifies an object's resistance to a push or a pull. A heavy boulder has high inertial mass, it is hard to get moving. A feather has low inertial mass, it is easy to move. The second phase is gravitational mass. This is the source of an object's gravitational pull, the m in the law of universal gravitation. For over 4 centuries, since Galileo supposedly dropped cannonballs from the Leaning Tower of Pisa, we have assumed these two masses are identical. They are equivalent. An object's resistance to acceleration is perfectly proportional to the gravitational force it exerts and feels. This equivalence principle is the bedrock of Einstein's general relativity. But what if, for some exotic component of the universe, this principle broke in the most extreme way possible? Imagine a substance whose inertial mass is negative. When you push it, it accelerates toward you, not away. When you pull it, it moves away. Its motion is reversed like a video played in rewind. Now couple that with its gravitational behavior. If its gravitational mass were also negative, it would create a gravitational field that repels ordinary matter. Positive mass objects would be pushed away from it. But here is the critical, mind-bending twist. If this exotic substance also obeys the equivalence principle, meaning its negative inertial mass equals its negative gravitational mass, then something extraordinary happens. 2 chunks of this negative mass material would repel each other gravitationally, but because of the reversed inertia, that gravitational repulsion would cause them to accelerate toward each other. It is a self-amplifying feedback loop of runaway motion. This bizarre behavior could, in theory, produce an accelerating expansion of space itself if such a fluid permeated the cosmos. The repulsion drives things apart, and the negative inertia ensures that drive only intensifies. In such a model, dark energy is not a property of space or a dynamic field. It is a bizarre, cosmic substance with backwards physics. The implications are staggering. Confirming negative mass matter would not just solve the dark energy puzzle, it would shatter our understanding of the most basic concepts in physics. The conservation of energy and momentum, the very stability of the vacuum, would be thrown into question. Could a universe with negative mass even exist without instantly flying apart or collapsing in a chaotic instability? The theoretical hurdles are immense, which is why most physicists view the idea with deep skepticism. It is often seen as a last resort, a wild idea to be explored only if all more conventional explanations fail. Yet, its very existence as a theoretical possibility highlights the desperate creativity at the frontier of cosmology. We have measured an effect so strange that respectable scientists are forced to contemplate matter that falls up and moves backward. It is a testament to the depth of the mystery that such radical surgery on the laws of physics is even on the operating table. The sheer weirdness of negative mass forces us to scale down our perspective. From the dizzying vastness of cosmic voids, we turn our gaze inward to our own celestial backyard. Could the shadow of dark energy, so dominant across billions of light years, cast even the faintest whisper here in the ordered orbits of our solar system? The answer hinges on a simple, brutal fact of scale. The average density of dark energy across the cosmos is almost inconceivably small. We often state it as about 10 to the negative 27 kilograms per cubic meter. To put that in human terms, a cube of space with sides the length of Earth would contain only about 400 grams of dark energy, less than the weight of a loaf of bread spread across a volume a quintillion times larger than our planet. Within the confines of our solar system, the gravitational influence of this diffuse energy is utterly swamped by the titanic pull of the Sun and the planets. The Sun's gravity creates a deep, commanding well in space-time, dictating the precise elliptical paths of every world, asteroid, and comet. Dark energy's uniform, repulsive push is like a gentle, planet-wide breeze trying to alter the course of a battleship. Its effect is theoretically present, but so infinitesimally tiny that for all practical purposes it is zero. We would never expect to see Mars or Jupiter drift from their predicted orbits because of it. The numbers are clear. Any acceleration imparted by dark energy on an object within our solar system is dozens of orders of magnitude smaller than the accelerations caused by the gravitational pulls of known bodies, or even by the subtle pressure of sunlight itself. So, in a direct, obvious sense, no, dark energy leaves no fingerprint on planetary motions we can currently measure, but science thrives on pushing the boundaries of the measurable. This leads to a more nuanced and fascinating quest. While dark energy cannot perturb planets, could its presence subtly alter the very fabric through which gravity's messages travel? This is where experiments of almost unimaginable precision enter the story. Consider the propagation of gravitational waves, the ripples in space-time from cataclysmic events like black hole mergers. These waves travel across the universe, and as they do, they are stretched by the expansion of space itself, a phenomenon called gravitational wave redshift. If dark energy is dynamic, if its strength has changed over time, it would leave a specific imprint on how that stretching occurs across different cosmic distances. By comparing the gravitational wave signal from a merger with the light from the same event, astronomers can create a new, independent measure of the universe's expansion history, a direct probe of dark energy's influence on the geometry of spacetime. Closer to home, other experiments search for deviations in the fundamental laws of gravity at extremely low accelerations. The grand dance of the solar system is the ultimate testing ground for Einstein's theory. Missions like NASA's Juno spacecraft orbiting Jupiter or the meticulous tracking of the Cassini probe at Saturn provide exquisitely precise data on planetary orbits and how radio signals are delayed and bent by solar gravity. Any persistent, unexplained anomaly in these measurements, after accounting for every known gravitational tug and relativistic effect, could be a hint of something new. It could indicate that gravity behaves very slightly differently in the weak field environment of the outer solar system, a regime where some modified gravity theories that mimic dark energy might manifest. Furthermore, laboratory experiments on Earth are now reaching sensitivities that brush against the frontier of the absurd. Using ultra-precise atomic clocks or delicate torsion balances, physicists look for minuscule variations in the local gravitational constant or test the equivalence principle with ever greater precision. While these experiments are not designed to detect dark energy directly, they are testing the bedrock assumptions of our theories. If dark energy is a sign of new physics, of a breakdown in general relativity or a new fifth force, its effects might first appear as a tiny crack in these foundational laws, even at small scales. So, while we will never see Pluto wobble because of dark energy, its ghostly presence motivates a global, silent hunt for deviations so small they defy belief. We are listening for the faintest echo of the cosmos's acceleration in the ticking of an atomic clock and the path of a laser beam sent to a distant spacecraft. The search tells us that the mystery of dark energy is not confined to the distant heavens. It is a puzzle being pursued in the most precise machines humanity has ever built. The silence of empty space is a lie. According to the rules of quantum mechanics, the vacuum is not an inert nothingness, but a seething, turbulent sea of potential. At scales so small they defy visualization, pairs of virtual particles and their antiparticles constantly flicker into existence, borrowing energy from the vacuum itself, only to annihilate each other and vanish back into the void an instant later. This quantum frenzy is not just a theoretical curiosity, it is a verified prediction of our most successful theories. The Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum experience a subtle attractive force, is direct experimental proof of these quantum fluctuations. The plates restrict the types of virtual particles that can form in the gap between them, creating a pressure difference that pushes them together. So we know this quantum vacuum is real and it is alive with transient energy. This leads us to the heart of a catastrophic mismatch. Every one of these fleeting virtual particle pairs contributes to the overall energy density of empty space. When physicists attempt to calculate the sum total of all this quantum jitter, from every possible particle type across all possible energy levels, the answer they get is not just large, it is monstrous. It is a number so colossal it is essentially infinite. To make it finite, they impose a sensible cutoff at the highest energy scale we think makes sense, the Planck scale, where gravity becomes as strong as the other forces. Even then, the estimated vacuum energy density is around 1 followed by 120 zeros larger than the dark energy density we actually measure from the accelerating expansion of the cosmos. This is not a small error. It is the worst theoretical prediction in the history of science. If the quantum vacuum truly held that much latent energy, the repulsive force would have been so unimaginably powerful that the universe would have blown itself apart in the first fraction of a second. Galaxies, stars, and life would have been impossible. The fact that we are here measuring a universe 13.8 billion years old means something is profoundly, fundamentally wrong. So we are forced to ask, what is the ultimate source of the specific, tiny vacuum energy we call dark energy? Why does the cumulative roar of the quantum vacuum translate into nothing more than a faint, persistent whisper in the cosmos? One terrifying possibility is that our mathematics is simply incomplete. The calculation that yields the gigantic number might be adding things together that should not be added, or missing a crucial cancellation mechanism. Perhaps the contributions from different types of particles and fields, from electrons to quarks to the Higgs boson and beyond, are not all positive. Maybe they come with opposing signs, positive and negative, and through some miraculous, unknown symmetry, they almost perfectly cancel each other out, leaving behind only the faintest residual energy we detect as dark energy. This would require a level of fine-tuning so exquisite it seems absurd, like balancing a mountain on the head of a pin. Yet, the alternative is that our understanding of the quantum world and the nature of empty space is fundamentally broken at its core. The vacuum energy we calculate might be a mathematical artifact, not a real, physical energy that gravitates. Or perhaps gravity itself does not couple to this quantum vacuum energy in the way we assume. Maybe the rules of general relativity, which tell us how energy curves spacetime, simply do not apply to this bizarre, fluctuating ground state of the universe. This is the ultimate standoff. On one side, quantum field theory, our master guide to the subatomic realm. On the other, general relativity, our flawless map of the cosmic scale. They meet in the concept of vacuum energy, and they violently disagree. Dark energy is the screaming evidence of that disagreement. Finding its true source is not merely about solving a cosmological puzzle, it is about healing the deepest fracture in modern physics. It asks us to discover what empty space truly is, and why its hidden hum is so quiet, yet powerful enough to steer the fate of all existence. This staggering failure of prediction, the vacuum catastrophe, is not just a mathematical inconvenience. It is a direct assault on our intuition about why the universe is the way it is. If the cosmological constant is so unnaturally, impossibly small, why isn't it zero? Or why isn't it the colossal number that should have destroyed everything? This fine-tuning is so extreme it feels like a cosmic prank, a setup. One radical, mind-expanding answer has emerged from the ashes of this paradox. Perhaps dark energy is not a puzzle to be solved within our universe, but a clue that our universe is not alone. Could it be a sign of a multiverse? To understand this leap, we must revisit the fine-tuning problem with new eyes. The constants of nature, from the strength of gravity to the mass of the electron, appear perfectly calibrated for a universe that can produce stars, planets, and life. Tweak any one by a minuscule amount, and the result is a sterile, empty cosmos. The value of dark energy is the most glaring example. It sits in a breathtakingly narrow window between two catastrophes, too strong and nothing forms, too weak and everything collapses. In a single, lonely universe, this looks like a miracle or a frustrating accident. The multiverse hypothesis offers a different kind of explanation, one rooted in probability rather than design. Imagine a vast, perhaps infinite, cosmic landscape where new universes are constantly bubbling into existence, each born with a random set of physical laws and constants. In this eternal froth, sometimes called the cosmic landscape, the strength of dark energy, the cosmological constant, would be different in every single one. In the overwhelming majority of these universes, the value would be enormous. Those universes would inflate and rip apart in an instant or collapse back on themselves immediately. They are stillborn, empty and dead, but in a vanishingly tiny fraction of the multiverse, by pure random chance, the cosmological constant would fall into that razor-thin slice of viability. In those rare, lucky universes, expansion is gentle enough and gravity strong enough that galaxies can form, stars can ignite, and given enough time, curious minds can evolve to look up at the night sky and wonder about the force accelerating their cosmos. We, of course, find ourselves in one of those rare universes. We could not do otherwise. This is the anthropic principle in its starkest form. We do not observe a universe fine-tuned for life because the universe was designed for us. We observe a fine-tuned universe because only in such a universe could observers like us ever arise to make the observation. In this view, the question, why is dark energy so small, has a simple, almost chilling answer, because if it were any other way, we would not be here to ask the question. Our universe is not special, it is simply survivable. This idea transforms dark energy from a profound mystery into a cosmic selection effect. The value we measure is not dictated by a fundamental law of physics, but by the silent, statistical requirement for our own existence. It is the signature of our address in the multiverse. This is not a testable theory in the traditional sense. We cannot, with our current understanding, peer beyond the boundaries of our own cosmic bubble to see the other universes in the landscape. But it makes a powerful, indirect prediction. If the multiverse explanation is correct, then we should expect to find other constants of nature also sitting in narrow, life-permitting ranges. The fine-tuning we see for dark energy would be just one piece of a larger pattern of anthropic selection. Furthermore, some versions of string theory, our leading candidate for a theory of everything, naturally predict a vast landscape of possible universes, each with different vacuum energies. In this framework, our universe with its tiny cosmological constant is not an anomaly, but an inevitability somewhere in the cosmic froth. The multiverse idea is deeply controversial. To some, it feels like a philosophical surrender, explaining one mystery by invoking an infinite number of others. Yet, it persists because it directly addresses the unbearable improbability that haunts modern cosmology. It reframes the question from why are the laws of physics this way, to what are the laws of physics that allow for a multiverse where our conditions can arise. Dark energy, therefore, might be more than a force shaping our future. It could be our first tangible piece of evidence that our reality is just one page in an infinite book, a single bubble in a froth of universes, each with its own forgotten story. The shadow of those earliest moments may still be with us, not as a field or a force, but as a ghostly relic. Primordial black holes are one of the most fascinating what-ifs in cosmology. They are not born from the collapse of a massive star like the black holes we know. Instead, they are thought to have formed in the chaotic furnace of the very early universe, when extreme densities could have squeezed pockets of space itself into singularities. Their existence is still hypothetical, but if they are real, they are cosmic time capsules, and their story may be deeply entwined with the forces that shape the cosmos, including dark energy. To understand this link, we must travel back to the first second of existence. In that seething, dense plasma, quantum fluctuations, tiny ripples in the fabric of reality, were stretched to enormous sizes by the hyper-expansion of inflation. In regions where the density was particularly high, gravity could have won out completely, causing a direct collapse into a black hole. These primordial black holes could have a staggering range of sizes, from as small as an atom to as massive as 1,000 suns or more, depending on when exactly they formed. This is where dark energy's ancient predecessor may have played a crucial role. The epoch of inflation and any other brief, violent expansion phases that might have occurred acted like a cosmic sieve. The rate and duration of that expansion would have determined which density fluctuations had time to collapse. A faster or longer inflationary period would stretch fluctuations to larger scales, potentially favoring the creation of larger primordial black holes. A different expansion history would produce a different mass spectrum, a different population of these ancient objects. So, if we could ever find and measure primordial black holes, their masses and distribution could serve as a fossil record of the universe's earliest expansion phases, indirectly probing the physics of vacuum energy in its most potent form. But the connection does not end in the past. Dark energy, in its current, feeble state, could influence these objects in the far future. Primordial black holes, especially the very small ones, are not necessarily eternal. According to Stephen Hawking's groundbreaking work, black holes can slowly evaporate, emitting radiation over astronomical timescales. For a hypothetical primordial black hole with the mass of a small asteroid, this Hawking radiation process would cause it to lose mass and eventually vanish in a final, faint burst of particles. Here, dark energy's relentless push could have a subtle, final say. As the universe accelerates, the density of matter and radiation plunges. A primordial black hole drifting in the emptiness of intergalactic space will find less and less material to consume. Its growth is stunted. More profoundly, the accelerating expansion may alter the very environment in which Hawking radiation plays out. Some theoretical models suggest that in a universe dominated by a cosmological constant, the event horizon of a black hole and the cosmological horizon of the universe itself interact in complex ways, potentially modifying the evaporation rate. While these effects are minuscule for any black hole we could hope to detect, they highlight a profound principle. Nothing in the cosmos is truly isolated from the background expansion. Even the darkest, most compact objects are subject to the silent tide of dark energy, their ultimate fate woven into the same fabric that is pulling galaxies apart. The search for primordial black holes is therefore a hunt on two fronts. It looks back to test our theories of the violent infant universe and its expansion. And it looks forward, asking how the universe's final era will treat its oldest inhabitants. Finding even one would open a new window, not just into black hole physics, but into the long and winding story of why our universe expands the way it does. The fate of the cosmos will not be decided by theory alone, but by light. Every mystery we have explored, from the nature of dark energy to the value of W and the reality of the Hubble tension, is now funneling into a single, monumental effort. The next decade will see the launch and operation of telescopes so powerful. They are designed not just to see deeper into space, but to read the history of the universe's expansion like a detective scrutinizing a timeline. This is not incremental progress. It is an all-out assault on the unknown, using the entire sky as our laboratory. Leading this charge are three revolutionary observatories, each with a unique strategy to corner dark energy. First, the European Space Agency's Euclid spacecraft, already in operation. Euclid is a cosmic cartographer on an epic scale. It will map the three-dimensional positions of over 1 billion galaxies across 10 billion years of cosmic history. But it is not just counting galaxies, it is measuring their shapes with exquisite precision. You see, as light from these distant galaxies travels to us, it passes through the warped space-time around massive clusters and filaments of dark matter. This gravitational lensing subtly distorts the galaxy's shapes, stretching them into tiny, coherent arcs. By analyzing the statistical pattern of these distortions across the sky, Euclid can create the most detailed map of dark matter ever made. This map is a direct record of how cosmic structure grew over time. If dark energy has been suppressing that growth, as our models predict, Euclid will see the precise moment and manner in which it happened, putting stringent new constraints on the equation of state W. On the ground, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, will take a different, breathtakingly comprehensive approach. From its perch in Chile, its giant mirror and massive camera will scan the entire southern sky every few nights, not once but over and over for a decade. It will create a colossal time-lapse movie of the universe. This relentless survey will discover billions of galaxies and, crucially, millions of Type 1a supernova, the very cosmic lighthouses that first revealed acceleration. But where past studies used hundreds of supernova, Rubin will deliver millions. This vast statistical power will allow scientists to trace the expansion history with razor-thin error bars, searching for any subtle drift in the value of W over cosmic time. It will see if dark energy truly is a constant or if its whisper has changed in tone. Finally, looking to the late 2020s, NASA's Nancy Grace Roman Space Telescope will combine the strengths of both. With a field of view 100 times larger than the Hubble Space Telescope, Roman will conduct its own massive surveys of galaxies and supernova. But it carries a special instrument designed for a technique called microlensing, which can detect isolated, rogue planets and even free-floating black holes. This will help us understand the population of compact objects, including the potential primordial black holes we discussed, which are part of the cosmic inventory. More directly for dark energy, Roman will perform ultra-precise measurements of baryon acoustic oscillations. These are frozen sound waves from the early universe, imprinted as a subtle, preferred distance between galaxy pairs. Acting as a standard ruler stretched by cosmic expansion, these oscillations allow Roman to measure how fast the universe was expanding at different epochs with phenomenal accuracy. Together, these observatories form a triangulation strategy. Euclid maps the dark matter scaffold, Rubin captures the explosive death of stars across time, and Roman employs the frozen echoes of the primordial cosmos. They will cross-check each other, eliminating systematic errors and building an indomitable case for what dark energy is and what it is not. They aim to measure W2 within 1%, a precision that could definitively rule out whole classes of theories. Will they find that W is exactly -1, cementing the cosmological constant? Will they detect a slight deviation pointing to dynamic quintessence, or will they uncover something entirely unexpected, a twist in the data that sends theorists back to their chalkboards? The data streams from these missions will be a fire hose of discovery, and in its flow, we may finally find the answers we have been seeking for a quarter of a century. The universe has kept its greatest secret for 13.8 billion years. Our generation is building the tools to ask it one final time to reveal itself. All these telescopes, all these surveys are chasing a phantom. We call it dark energy, but the name itself may be the greatest misdirection of all. We have spent 25 questions searching for a thing, a substance, a particle, a field. But what if we have been asking the wrong question from the very beginning? The final, and perhaps most profound, unsolved question about the universe's expansion brings us full circle, back to the very stage upon which the cosmic drama plays. It asks us to reconsider the ultimate nature of space-time itself. The accelerating expansion may not be caused by something in space-time. It may be a fundamental property of space-time. Think of it this way: for a century, Einstein's general relativity has taught us that space-time is a dynamic fabric, curved and warped by the mass and energy within it. It is the canvas, but what if the canvas is not passive? What if it possesses an intrinsic dynamic tension of its own, a kind of elastic energy that causes it to want to stretch, to expand, all on its own? In this radical reframing, dark energy is not a mysterious actor on the stage. It is the stage itself, restless and self-accelerating. This perspective transforms the mystery from a hunt for a missing component to a crisis in our foundational physics. Solving cosmic acceleration will not be about discovering a new particle in a detector. It will require a new theory of gravity, a deeper understanding of quantum mechanics, or a revolutionary synthesis of the two that reveals what space-time truly is at its most fundamental level. Our current models treat space-time as smooth and continuous, like a perfectly flat sheet of rubber. But at the quantum scale, many theories suggest it is nothing of the sort. It may be a seething foam, a digital lattice, or a tapestry woven from discrete, vibrating loops. Could the large-scale acceleration we see be a collective effect of this quantum graininess? Could it be that, when averaged over the vastness of the cosmos, this churning, foamy nature of space-time naturally produces a repulsive effect, an inherent tendency to expand? Imagine a fluid that is never still. At the microscopic level, it is a chaos of vibrating molecules, but pour it into a vast basin, and you see smooth, large-scale waves and currents. Dark energy could be the smooth, large-scale wave emerging from the quantum chaos of space-time's true texture. We have been trying to explain the wave by looking for a separate source of wind, when the wave is simply how the ocean breathes. This is the ultimate challenge posed by the runaway universe. It forces us to accept that dark energy is less a thing and more a symptom. It is a glaring symptom that our understanding of reality is incomplete, that our map of gravity and the cosmos is missing a continent. The cosmological constant, quintessence, modified gravity, these are all attempts to patch the map. The real discovery will come when we realize the map's very geometry is wrong. When we finally peer into the heart of this mystery, we may not find a dark substance. We may instead discover that space-time is a dynamic, self-interacting fluid, and its natural state, when empty of matter, is not stillness but a gentle, relentless stretch into the infinite. The acceleration is not an anomaly. It is space-time's own signature, written in the fading light of every distant galaxy, waiting for us to learn how to read it. We stand at a precipice, staring into a cosmos where the questions outnumber the answers. These 25 unsolved mysteries about the universe's expansion are not isolated curiosities. They are threads in a single, colossal tapestry of ignorance woven from the same dark fabric. The accelerating expansion is the central, defining challenge of our cosmic era. It is a problem so deep that its solution will not merely fill a gap in our knowledge, it will shatter the textbook and demand we write a new one. Whether the answer lies in an exotic new energy, a fundamental rewrite of gravity, or a leak into unseen dimensions, the discovery will redefine reality itself. This is not a passive mystery. It is a race, a global, collaborative sprint to understand the engine of the cosmos before the final chapters of our story are written in darkness. The greatest telescopes ever built are now scanning the sky, their digital eyes collecting light that holds the secret. The most brilliant minds are wrestling with equations, searching for the key. And you are here, witnessing this moment. The story is unfolding in real time. This is an invitation to stay curious, to follow the journey as the data pours in and the theories rise and fall. The vast, overwhelming majority of our universe, 95% of everything, remains utterly unknown to us. It is a humbling and thrilling truth. We live in a sliver of light surrounded by an ocean of darkness, and we have only just begun to dip our toes in the water. The next breakthrough could come tomorrow from a telescope's fresh data or a theorist's midnight insight. And when it does, it will change our place in the cosmos